So example number 3, set up a triple integral that can be used to find the volume of the ellipsoid given by this equation. 9x squared plus y squared plus 9z squared equals to 9. Okay, so that's it. They're not telling us any limits. They're not giving us anything at all. How are we going to set this up? Well, so number 1, I would like to write the equation in a more known way, in a different form. So that is, I'm going to divide both sides by 9 to get x squared plus y squared over 9 plus z squared equals 1. That is in the form x squared over a squared plus y squared over b squared plus z squared over c squared equals 1. This is going to give us an idea of the limits, or rather, not the limits. Well, yes, the limits as well, but also the intercepts of the surface here that we can use to graph it, although you're not expected to graph this. You're not expected to graph this surface. It's one of those surfaces hard to plot. Unlike a plane, for instance, a cone, maybe the sphere at an octant, a parabola. Those are easy to plot, but not an ellipsoid. Instead, I have GeoGebra to help us out. Okay, so this is the ellipsoid we're looking at. So, well, number 1, this means the x-intercepts are plus or minus 1. The y-intercepts are y equals plus or minus 3. And the z-intercepts are, again, plus or minus 1. Right? Let's verify that graphically. So I have typed the same function here, 9x squared plus y squared plus 9z squared plus 9. And we can see the intercept here is the x-axis. Along the x-axis, we have plus and minus 1. Along the y-axis, plus and minus 3. And along the z-axis, see how we go from negative 1 to 1. All right, those are the intercepts. They're verified graphically here. All right, let me get rid of this plane. Thank you. All right, so what do we need to know? So regardless of the shape that you're given, we need to see what's going on in the XY plane. So forget about the solid, forget about everything. What's going on in the XY plane? Well, so of course, I'm going to rotate the graph so we can see what's going on in the XY plane. We can see it's an ellipse, right? Let's write that ellipse. How do we get that algebraically? Well, so number 1, I'll make z equals to 0 because I will need to look at the intersection between the surface in space and the XY plane. That is by setting z equals to 0. So that's going to leave us with 9x squared plus y squared. Let me use the other form instead. So that is x squared over 1 plus y squared over 9 plus 0 squared over 1 equals to 1, which will lead to x squared over 1 plus y squared over 9 equals to 1. So that'll be an ellipse, right? That will be the ellipse projected onto the XY plane with x-intercepts plus and minus 1, and y-intercepts y plus and minus 3. Okay? So what can we do from here? Well, that's our projection onto the XY plane. Let me plot that real quick. So it's gonna look like this roughly. Okay, that's good enough. So okay, so this is minus 3, 3, minus 1, and 1. All right, well, what are we going to have here? If we solve for y for this equation here, that's going to leave us with y squared equals to 1 minus y squared over 9, rather, 1 minus x squared, and then multiply both sides by 9 to get y equals, or rather y squared equals to 9 minus 9x squared. And then y would be
the square root of 9 minus 9x squared.
I know you could factor out a 3 if you want, that's fine. Let's leave it like this for now.
Well, actually, this is plus minus, right? What is this plus minus going to mean? Well, here, the upper part of the ellipse will be y equals the square root of 9 minus 9x squared, while the bottom part below the x-axis, that's going to represent the negative radical. All right?
That represents the negative radical. So that's going to help us set up the limits of integration for the outermost two integrals with respect to y and with respect x. All right? So with respect x, I think the limits are pretty obvious. -1 to +1. Now, what's going on in space? Okay, so let me do the same here. So let me keep solving. I'm going to solve for z right here. So z squared equals 1 minus x squared minus y squared over 9. And then z equals to plus or minus the square root of all this madness here. 1 minus x squared minus y squared over 9. Right? Well, since in this case these are functions, it's two functions, a plus and a minus, plus radical minus radical, that represents number one. The positive, I think it's obvious that it's going to represent the roof, the roof, and the minus is going to represent the floor of the solid. So how come? Well, let me go to the solid in GeoGebra here. So okay, let me put this perspective. That's the typical 3D perspective. Okay, so this is going to be the bottom part, and this is the top part right here, represented by the the positive radical and negative radical. All right. So we have, I think we already have everything we need to to set up the integral. And just to have a better visual, I have parameterized the curve of intersection between the ellipsoid and the xy plane, which is this curve right here. So how did I parameterize this curve? Well, so this is a curve on the xy plane. So that means what we can parameterize in a similar way we parameterize circles, cosine and sine, where the variable, well, I chose u to be the variable, could be t, could be v, could be the symbol theta, either way, doesn't matter. And I chose it to go between 0 and 2 pi for 1 to make it traverse once, all right? And while the coefficients 1, the invisible 1, and 3 represents the intercept given in the equation, right? So, all right. So let's go back to the problem. Let's go back to the notes and set up the integral. All right, let's write the domain of integration first. This is going to look big, okay? So that is the domain. That'll be the set of all order triples x, y, z, such that, okay, x is going to vary between -1 and 1. Y, so here we have the y limit in green, that is negative root of 9 minus 9x squared, and positive square root of 9 minus 9x squared. And lastly, the limits for z, I think they're here in yellow, right? So that is a negative root of, what's that? 1 minus x squared minus y squared over 9. Z equals square root of 1 minus x squared minus y squared over 9. All right? So that is our domain of integration. And guys, for many of the situations for triple integrals, more precisely when we get to what you call cylindrical and spherical, you won't be required to write the domain in this notation because it won't be that easy to come up with. So you will just be asked to find the domain in the new system. Okay, so volume v equals to the triple integral over the region, let's call it d, or yeah, it's d, right? That is, okay, the integral from -1 to 1
from negative root of 9 minus 9x squared to positive root of 9 rather minus 9x squared, and then the third integral from negative root of 1 minus x squared minus y squared over 9 to root 1 minus x squared minus y squared over 9 dv. And that's going to be our triple integral that would calculate, oh, I need to iterate this, by the way. It has to be dz, dy, dx. All right? Is there an easier way or a more compact way to express this triple integral? Yes, there is. What if instead, check this out, integrate between 0 and 1, between 0 and the positive radical, right? And between 0 and the square root of 1 minus x squared minus y squared over 9. All right? dz, dy, dx. Okay, so notice I put zeros for the lower limits of integration. But what should we do with this integral? By 2? Think about it. By 6.
By 8?
By 8. Why by 8?
Well, because we have like a triple integral, so we're kind of like, we need to double it 3 times. So.
Okay, in terms of powers of 2, or yeah, I see what you mean about that. But geometrically speaking, why by 8? Okay, this is right, by 8. Okay, that's final answer. But why? Yeah, 2 times 2 times 2 equals 8. Yes. Because they're 8 octants. So what am I doing here? So all I'm doing here is I'm considering, okay, between 0 and 1, and between 0 and the positive radical, that's only this region. So that's the first quadrant, right, in the xy plane. But well, first quadrant in the xy plane means first octant in space. So really we're finding the volume in the first octant. First octant, second octant, third octant, fourth octant. There's 4 octants plus another 4 below equals to 8. All right? So either way, I mean, you don't have to use the symmetry property here. That's fine. Either way, that will be okay. All right. Let's have a look at another example, another setup problem. Okay. Set up a triple integral that can be used to determine the volume of the solid bounded below by a cone and bounded above by a sphere. Okay. What is that going to look like? That's going to look a lot like an ice cream cone. Okay, so reset. We find it. So there you go. Right. Hey, there you go. So this is how it's going to look like. So let me see if I can turn all this off. Okay, yes. So we can see what's going on. So we have this sphere. Do I have the equation of the cone? No, I don't have it. Let me type that real quick. So that'll be z equals to the square root of x squared plus y squared. All right. So that's that's what we have right here. But I mean, the problem with GeoGebra oftentimes is that we get to see the entire surface, is not only what we're interested in. So I mean, it's a little hard to see the intersection between this cone and the circle, right? So, but still, well, I have everything ready here. So like, is this the actual? Okay, this is the one. Yeah. Here, this is the circle that intersect, that actually represents the intersection between the cone and the sphere, right? What else do we have? So let me draw this. Is that a surface? No, not this one. Okay, is that this part of the surface? Because in this case, I don't want the entire circle. I only want the circle, the entire sphere. I only want the part that is above the cone, which is this part in green. And I don't want this. Let me get rid of this sphere. And I don't want the entire cone. So I just want this part right here. So let me get rid of that part of the cone. So that's going to give us this solid. Okay. Now, if I rotate this solid and in a way that I can see the XY perspective, you'll see that the region of integration, it's a circle, right? It's a circle of radius. Well, it's not clear to me here. It's not 4, it's somewhere between 4 and 5. Well, that's from the solid perspective. I have another, let me get rid of this. So you have this curve right here. So for instance, what we can do right here is slam this this curve to the XY plane, and that'll be the projection. This would be the shadow of this intersection between the cone and the sphere. And I think it will be a lot easier to see what's going on. So, and yes, I mean it's between 4 and 5, but it's not quite 4.5. So we need to get this algebraically, all right? So let's go ahead and do the algebra required so we can set the limits, because, well, you'll see why. So number 1, what do? Well, so number 1, let's algebraically find the intersection, the intersection curve between the cone and the sphere. That is, because this is z squared equals to 40 minus x squared minus y squared, and z equals, well, actually, should I? Let me leave it like this. Let me square both sides here, so we get z squared equals to x squared plus y squared. All right, now, z squared. How about we set the z squareds together, right? Rather than working with radicals and the like, let's just do the z squareds. So that means set x squared plus y squared equals to 40 minus x squared minus y squared. Okay, so x squared plus y squared equals to 40 minus x squared minus y squared. Let's move all the squared terms to the left hand side. That'll be 2x squared minus 2y squared, or rather plus, equals to 40. And let's reduce everything by dividing both sides by 2. That's x squared plus y squared equals to 20. Isn't that the equation of a circle? Yep. So what's the radius of that circle? Well, that's 20 is not a perfect square. So let me write this like, so the center, which is the origin, and the radius, which is root of 20. But what is the square root of 20? Is that 4 times 5? Is that 2 root of 5? 2 root of 5. Okay, what is 2 times root of 5? Can someone help me with the calculator? What's that? It should be 4 point something, right?
4.47.
4.47, right? 4.47. Doesn't that look a lot like that 4.5 from the GeoGebra picture? Yes. Yeah, 4 point. So it's almost halfway through, right? It's almost halfway here, but not quite. Just those 3 decimals there, right? Just those 3 decimals. Okay. What do we have so far? So we have the intersection curve. Okay. So let me plot that intersection curve here. Okay. Let me plot the circle right here. Okay. So what are we going to have right here? So number 1. From here, we get, no, that's not what I wanted. There we go. So we're going to get the following. That is, y squared equals to 20 minus x squared, which is y equals to plus minus the square root of 20 minus x squared. what is that going to be? Well, plus minus, that's going to represent the upper semicircle for the positive radical, and the lower semicircle is going to be represented by the negative
radical. All right. Well, what about the x-intercepts? The x-intercepts are going to be
this plus minus negative root of 20, root of 20, or 2 root of 5, either way.
All right. So when we set up the integral, we will decide maybe the most simplified version.
Okay, so I think we already have everything we need to, number one, set up the domain of integration, and then set up the triple integral. All right.
Okay.
So let's set up the domain. Number one. So I'm gonna call it this time Q. Let me call it Q, which is the set of all order triples x, y, z, such that, well, let's start with x. X varies between negative 20 or negative root of 20 to root of 20. Looks like a 26, okay. Then y varies between negative the radical, 20 minus x squared, to 20 minus x squared. But what about z in this case?
Well, that's again the highest surface minus the lowest surface. Well, on the note, well, we can see that. However, that's why we have GeoGebra.
And, well, it's gone. Oh, there you go. So let me get rid of this. Okay, let me actually highlight the surfaces. So in this case, which surface is the upper, which surface is the lower? Cone is the lower and bounded above by the sphere, or by that part of the sphere. Okay, so that means, in this case, z will vary between the cone and above by, what's that? The sphere, for which I will use the solved version, I guess. Oh, careful, because, okay, here z equals plus or minus the square root of 40 minus x squared minus y squared. So when we solve for z, we get two expressions, one positive, one negative, because of the square root property, you know, the algebra behind. However, one of those will be the relevant one. Which one do you think is going to be the relevant one? The positive one or the negative one? The positive, because it's the upper hemisphere, right? So that is 40 minus x squared minus y squared. All right. And let me close with curly braces.
And we're ready to set up the triple integral that will calculate the volume of this intersection between a cone and a sphere. So volume again.
Volume, that's the triple integral over the region Q dv. Again,
there is an invisible one in the integrand. That means this triple integral represents volume. But if you have something other than a 1, that's going to calculate a different quantity that we'll discuss later in the next couple of sections, not in the next one.
All right. So, okay, that'll be the triple integral, well, from negative root of 20 to positive root of 20, from negative root of 20 minus x squared to root of 20 minus x squared, and from what's that? From the cone below, x squared plus y squared to the square root of 40 minus x squared minus y squared. And we'd better iterate this way, dz, dy, dx. All right?
So that's one way to set up our triple integral. Okay, so another way to rewrite this integral so that we can simplify some of the work. I mean, if we were to evaluate this triple integral, and rather by taking advantage of the symmetry of the solid, because clearly there is some symmetry, right? Clearly there is some symmetry here. I mean, it's symmetric about the x-axis, it's symmetric about the y-axis, so it looks like we could find the volume of this ice cream cone by simply finding the area. I mean, finding the volume in the first octant right here and multiply that by 4, right? Some of you did it by multiplying by 8 and getting rid of the cone, having the lower limit in the inner integral being 0. But if you do that, you will be no longer finding the volume bounded by the cone part. You still need to have that cone part. Okay, so let's see. We go back to the notes, and that'll be, so the integral from 0 to root of 20, the integral from 0 to square root of 20 minus x squared, and the integral still from the cone to the upper hemisphere. All right, dz, dy, dx. All right, and then did we multiply this by 4? Yes. Okay. Now, is there a way to do this so that we still multiply by 8? Well, yes, there is. Now you need to be careful, because what are we given? So we are given the equation of the cone as only one positive radical. However, there could be situations in which we would be given the equation like this: z squared equals to x squared plus y squared. That'll be different. All right? That's because in this case, when having this z squared inside another radical, we would have two cones, one above and one below. How does that going to look like? Okay, let me get rid of this. Let me create another GeoGebra project here. Okay, don't save. And instead, okay, there is a big difference between, let me show you the difference. So, there is a huge difference between having z squared, z equals to the square root, what's that, x squared, plus y squared. Oh, I forgot to get the solid version. Yeah, the 3D version. Yeah, 3D graphics. Okay, so show plane. Okay, I don't want a plane. Z equals to the square root of x squared plus y squared. All right. So that's just the upper cone, the one given by the radical. But what if I had the minus? I would have the cone below. And well, where can I get the plus or the minus below? Potentially from solving this z squared equals to x squared plus y squared for z. But in this case, we're only given the upper part. So now, let me get rid of this radical. And instead, let me square the z. Do you see the two cones, one above, one below? We would have the same sphere. Okay, let me write down the sphere. Okay, that is x squared plus y squared plus z squared equals to what? 40? Do you see how we have the same shape above and below the xy plane? And under this situation, you can multiply by 8 and have the volume of two ice cream cones, one above, one below. But it's not the case. That's because of the way that we're given the equation of the cone right here, which is by the positive radical. So in a different situation, if you were given this version, the z squared equals x squared plus y squared, you would need to think that you have two cones, the one above and the one below. Okay? Very different situations. Okay, what's next? Let's have a look at another setup problem. So, set up a triple integral that can be used to determine the volume of the tetrahedron
in the first octant bounded by the plane, 2x plus 6y plus 3z equals to 12. Okay, I don't have a GeoGebra project for this because the plane is easily plotted, using the intercept. Okay, so let me solve for, well, I'm not going to solve for a z yet. Let's first plot the plane. Okay, let me plot the plane. So we have x-intercept 12 over 2, is that a 6? And then the y-intercepts, that's 12 over 6, that's 2. And the z-intercept, that's 12 over 3, which is 4. All right, let me plot the surface. So that is the portion of the plane in the first octant. Well, how do we know that it's going to be only the portion of the plane in the first octant? Because they're telling us the coordinate planes. That is x equals 0, y equals 0, and z equals 0. The wall x equals 0, the wall y equals 0, and the floor z equals to 0. All right. So let me see if I can highlight using different colors so you can see that. So that's the floor in green. That's this wall for the xz plane right there. And this other wall right here for the yz plane. Okay? And this would be our solid right here, right? Okay, so I think it's going to be with this picture, hopefully it's a little obvious, maybe not that obvious, that the floor is z equals to 0 and the roof, it's the plane given by the equation that we're provided. That is, we would need to solve this for z. Okay, so solve for z. That is 3z equals to 12 minus 2x minus 6y. Z equals to, that's going to reduce to 4 minus 2/3 x minus 6 over 3, that's 2y. All right? So that is our surface, our plane surface in terms of a function of x and y. So what else do we need? So x equals 0, y equals 0, and z equals 0. This means, let me label this. This is the yz plane. This is the xz plane. And this is the xy plane. That is the walls in color right here. So the yz plane, that's actually in red. Let me change color so you can see the yz plane. That is this wall in red. And then the xz plane, this one is in yellow, that's fine. And then the xy plane, that's in green. All right? Just to color code what we're plotting versus what we are denoting here. Okay, so I believe we have no, not yet. We still need to see what's going on onto the xy plane. That is, okay, let me plot a 2D plane, a Cartesian plane, and I'm going to project this floor right here, where y equals to, what's the y-intercept? It's equal to 2, and this is equal to 6. Well, so this means if this line right here, this diagonal line, it's actually the what's it called, the xy trace, where we get the z equals to 0. That is, so xy projection. That is the xy trace, where z equals to 0. Where z equals to 0, that leaves us with 2x plus 6y equals to 12, because we no longer have the z term. That's because z equals to 0. Let's solve this equation for y. Solve for y, that is 6y equals to 12 minus 2x. And y equals to 12 over 6, which equals to 2, minus 2 over 6, which equals to 1/3. All right? So that'll be our upper limit minus lower limit in terms of y. Y equals to 0. Y equals to
2 minus 1/3 x. And the limits in the direction of x are going to start at x equals to 0 all the way to x equals to 6. And I believe we have everything we need to set up the triple integral. All right? So, again, volume will be the triple integral, what's that? dv over the region Q, or the region D, which, by the way, I still need to write that in set notation. Hold on. So, the domain D, that is all the order triples x, y, z, such that x varies between 0 and 6, y varies between 0 and 2 minus 1/3 x. And lastly, z varies between also 0 and the equation in terms of x and y that describes the plane. That is, what's that? 4 minus 2/3 x minus 2y. So that is our domain of integration. And those are going to represent the limit of integration when we set up the triple integral. All right? Volume then equal to the integral from 0 to 6, from 0 to 2 minus 1/3 x, and from 0 to 4 minus 2/3 x minus 2y. dz, dy, dx. And well, in this case, there's no way to write this like 4 times the double integrals, or 8 times, triple integral, or 8 times the triple integral, because, well, think about how this plane extends on the remaining octants. It doesn't create a symmetric solid, unlike the intersection between the cone and the sphere, or like the ellipsoid we did at the beginning of the lecture. So this one is different. This is a non-symmetric shape, so this is the only way to set up this triple integral. All right? Okay. Let's have a look at the next example. Let's see what it is about. So, in the same way as with double integral, it may be helpful to reverse the order of integration. But again, we did analyze this last time. Well, not last time. On Wednesday. The number of ways we can evaluate a triple integral. There's a total of 6, right? Total of 6 different ways to evaluate a triple integral. However, we're going to take into consideration only 2, starting with z only, and then either dy dx or dx dy. If we change the other orders, it may get a little complicated to see the projections no longer onto the xy plane, but rather onto the yz plane or onto the xz plane. That doesn't mean we're not going to do it at all. Actually, when we get to surface integrals, almost at the end of the course, we're going to evaluate integrals in such a way, but not for now. Okay, so suppose we want to find the volume of the solid region Q given by Q, where x is varying between 0 and 2, y is varying between x squared and 4, and z is varying between 0 and 2 minus x. All right? Write the triple integral using dv, dz, dy, dx. Okay? That is simply, in a straightforward way. That's all we want, in a straightforward way. So that is volume again. That's the triple integral over the region Q, dv, and the limits are simply 0 to 2, x squared to 4, and 0 to 2 minus x. dz, dy, dx. All right? Now, how does this solid look like? Okay, I believe I also have a GeoGebra project for this. Let me have a look. I remember I had it. Volume, triple integral. Yes, I hope this is the one. No, not here.
here. Mm-hmm. This is the one. Yes, this is the one. All right. So here we have x plus y equals to 2, or rather x plus z, not x plus y. That's x plus z in this case. Let me, yeah. So we have this plane right here. Is that x plus c? Yeah, that's the plane. So if we were to look at this, these two cylinders here, see what do I mean by cylinders? Well, again, recall that when we're looking at functions of multiple variables, when we're missing one of the variables, one of the three variables, that means we get, say, a parabola or a circle or whatever the shape extended along the axis that has the variable missing in the equation. That's what we call a cylinder. For instance, here this is what's that? X squared, y equals to x squared. But in this case, we have this parabola right here created by this solid right there, and so I have created here the intersection between these two surfaces. All right. So that means, let me get rid of these two. That's going to create this solid bounded by these two, right? Okay, so, well, I actually will post this project on Canvas later in case you want to go back and rotate it, see the projection onto the XY plane, etc. So, let me go back to the notes. So, let me plot this in the first two limits of integrate, or the first two inequalities right here will give us the limits, or how it's going to tell us how the projection onto the XY plane is going to look like. Okay, so that means, because now we need to rewrite the integral in a different order, still starting with dz, but we will reverse the dx dy to the dy dx to dx dy. So what do we have? We have, in the y direction, bounded above by the horizontal line y equals to 4, and bounded below by the parabola y equals to x squared. However, we don't want both sides of the parabola. That's because the limits of integration in the direction of x only go between 0 and 2. That means we're only interested in this region here, all right? Only that part of the projection onto the xy plane. So here, okay, let me label again, y equals to 4, y equals x squared, 0 to the intersection between x squared and 4, isn't that x equals to 2? All right? So what do we need to do this time? Because we have functions of x, that means we're looking at this region as a vertically simple region. Let's look at, by reversing it to the order dx dy, that means we need to look at this region, visualize this region as horizontally simple. That means we need functions of x. Let me rewrite this, y equals to x squared, as x equals the square root of y. All right? So that means the new domain of integration, d, oh no, that's q, right? That equals x, y, z, all the order triples x, y, z, such that, well, x this time is varying between 0 and root of y. Y is varying between 0 all the way up to 4. And lastly, for the z limit, there's no change. It's still the roof minus the floor given by this inequality here. That is 0 to 2 minus x. That doesn't change. Let's just rewrite the triple integral for volume. That is the triple integral over the region Q dv, Q dv, the integral from 0 to 4, from 0 to root of y, and from 0 to 2 minus x dz, but we're no longer going to do dy dx, we're going to do dx dy. If we were to evaluate this triple integral, both of them should give us the same result. One may be harder than the other one may be easier than the other one, who knows? All right? But just by looking at the limits of integration, they should be about the same level of difficulty. I don't see any reason why to change the limits of integration other than just visualizing how do we do it with a triple integral anyway. All right? Okay, so just to wrap up the section and take a break, why not look at average value of a function for 3 variables? So you might remember how for the case of a single integral, f bar, that equals the integral from a to b of f of x dx times 1 over b minus a. And then what did we do for f bar for a function of 2 variables? Well, that is the double integral of f of x y dA times 1 over the area of R when we integrate over R. Well, in this case, I'll make this easier to read. 1 over area of R times the double integral over R for the function f of x y dA. Well, that area may be calculated in 2 different ways. I mean, if we're integrating over a nice and simple rectangular region, just use geometry, length times width, or length of the side quantity squared if it's a square region. However, if it's not a simple region, then we would have to calculate that using another double integral that represents the area. That is, without the f of x y here, with a 1 in the integrand. So again, what I'm trying to say here, this division right here, it's 1 over the area. B minus a, that's the length of the interval. What do? Go from length, 1 dimension, to area, 2 dimensions, triple integral, 3 dimensions, volume. All right? So let's just have a look at one example and see what we get. All right? So find the average value of f of x, y, z equals z cubed plus 4 over the rectangular prism in the first octant bounded by the coordinate planes. That is x equals 0, y equals 0, z equals 0. Let me write it down. Okay, let's write that down. And the planes x equals 2, y equals 0, y equals 3, and z equals 4. This one should be easy to plot, by the way. That is x equals 0, y equals 0, that is 1, 2, 1, 2, 3, and 2, 3, 4. Okay, so that'll be, it's going to look like a rectangular box like this. Right? That is 2, 3, and 4. Okay, f bar. That is the average value of the function. That is 1 over the volume of the region D, okay, times the triple integral of f of x, y, z, dv. Okay, so for the volume of this solid region, well, in this case, we don't have one of those crazy solids that we have been looking through during the past exercises. We have a pretty nice rectangular box for which we can get its volume by just multiplying length times width times height, right? 2 times 3 equals to 6 times 4, 1 over 24. times the triple integral, all zeros, 2, 3, and 4, for the function z cubed plus 4. Because we iterated in this order, we're going to write dz, dy, dx. All right? Okay. So let's have a look at this integral. Let's evaluate it. So number 1, that is 1 over 24 times the integral from 0 to 2 and from 0 to 3. Well, let's integrate. Z cubed, that's going to give us, what's that? Z to the 4th, or 1/4. Z to the 4th, plus 4z. Evaluate that between 0 and 4. dy, dx. Let's apply upper limit minus lower limit. Okay, I know, big quantity. 4 raised to the 4th power, that's a big number. But how about, okay, well, let me write it down. 1 over 24 times the integral from 0 to 2 and from 0 to 3. That is 1/4 times 4 to the 4th plus 4 times 4 minus, how about 0? Because if we apply the lower limit of 0, all terms have the variable 0, so just gonna be 0. dy dx. Okay, don't use your calculator to evaluate this number. Okay, this is 4 to the 4th power. Divide that by 4. Isn't that going to be 4 to the 3rd power now? Which is an easy number to calculate in our heads. Isn't that 64? So that's 1 over 24 times the integral from 0 to 2 and from 0 to 3 of 64 minus 4 times 4, which is 16. 64 minus 16, is that, plus. No, it's not minus, it's plus actually. That's going to give us 80. Okay, so that'll be 1 over 24, the integral from 0 to 2 and from 0 to 3, times 80 dy dx. Okay, let me take that 80 outside of the integral. That'll be 80 over 24, integral from 0 to 2 and from 0 to 3, dy dx. The rest of the problem will be integrating simply along y, that's 3 minus 0, and then 2 minus 0. Well, let me do one integral at a time to show all the iterations. That's from 0 to 2, and that's y from 0 to 3 dx. That is 80 over 24, integral from 0 to 2, 3 minus 0 dx, which is simply 3. I can divide out the 3 divided by 24, is that 8? That is 80 over 8, integral from 0 to 2 dx, which is 10 x from 0 to 2. That is 10 times 2 minus 0, which is 20 units. All right, 20 units. Okay, so just to wrap up the section, let's briefly discuss what about triple integrals for which the integrand is no longer a simple one. Because for the last exercise we've been looking at triple integrals that represent volume. That is when the function equal, or rather the integrand is a 1. However, when it comes to having a different function, these functions may represent density function. So we would be finding the mass of the solid. That's because, well, from chemistry, density equals mass over volume. If you solve for mass, that is density times volume. What is that? Isn't that a density function times a volume differential? So density times volume equals mass. All right? However, that's going to be discussed in section 16.6, not in this section.